Today's tutorial is going to talk you through the Spearman's rank test, another statistical test that is going to tell us a little bit more than perhaps chi-squared did, but it's a little bit more complex. But hopefully the step-by-step guide here will simplify that process. It's worth noting that in a geographical investigation, often the chi-squared test would be conducted first with a set of data because it is relatively straightforward to see if there's any variation before we then start looking at correlation tests or looking to see if there are significant differences between groups of data. So, as I say, the Spearman's rank test is a correlation test, and it is looking to see whether data that you could plot onto a scatter graph is positive, whether it is negative, or indeed if there just appears to be no correlation between the data at all. The Spearman's rank equation is this one just up here. RS denotes Spearman's rank. The equation is always going to lie somewhere between 1 and -1. So that's a really good thing to keep in mind because it will straight away identify whether you have got something wrong. So for example, if you've gone through the process, your Spearman's rank value is 3.2, that won't fit. A perfectly positive correlation will return a Spearman's rank value of +1, and negative correlation will return a Spearman's rank value of -1, and if there's absolutely no correlation at all, we'll get a Spearman's rank value of 0. So of course, the closer to +1 or -1 your result is, the more significant the relationship between X and Y will be. As with all all statistical tests, we have to have two robust hypotheses. The null hypothesis, if you remember, is that there is nothing going on in our data. So in this instance, there is not a significant correlation between X and Y. And the alternate hypothesis is that there is a significant correlation between X and Y. For the purpose of this tutorial, I'm going to take a look at a physical investigation where a group of students have visited the River Glaven in Norfolk, and they were assessing whether there's a relationship between the depth of a river and its flow velocity. So they collected data out in the field, and their assumption would be that the depth of the river would influence flow velocity. So the depth of the river is their X data set, and the flow velocity is Y, because the assumption would be that a deeper river will result in a faster flow velocity. Okay, so I'm going to talk you through how we're going to set this out. We need to create ourselves a table, and in this investigation, the students gathered 10 different sites of data, which are listed down here. So they measured the depth of the river at its deepest point of 0.26 meters, 0.519, and so on. And at each of those points, they recorded its average velocity in Qmex. So there are two columns that we're listing first. Now, the assumption will be, if we just go back to the graphs, if there's a positive correlation, if we say here depth and the velocity, the shallowest measurement will also record the lowest velocity. The second shallowest section of the river will record the second lowest velocity, and so on until we get to the deepest part of the river, which we expect would flow fastest. So in this instance here, the rank value of 1, so the lowest, is also the rank value 1 here on the velocity, and the highest figure, so the deepest part of the river, would be the highest rank value, and likewise that will correlate with the highest rank value here. So the test is going to be looking to see if there's a difference between the rank values in the data collected. So the first thing that you need to do is rank the values on the depth. So we'll start off with the shallowest point in the river, which is here. Move to the second. Now, as you go through the ranking, this has been relatively straightforward so far. You may get to a point where there's two pieces of data that would be ranked equal. So number 7 after 0.519 is going to be 0.55. We see down here there's a second value which is equal. So what you would do is you would then rank those as if they were different and then take the average rank value. The average of 7 and 8 is 7.5. If there were three figures which were equal, you would list them, for example, 7, 8, 9, and the average rank value therefore would be 8. Okay, so we've now got some numbers that we will start to use that we can put into the Spearman's rank equation. You will note on the second ranking, where we're ranking the velocity, there are again 2 points where the average velocity is recorded as being equal, with 3.17 qx. So again, these have been ranked separately, and then the average has been recorded. So 6 and 7, the average point there would be 6.5. Now, the next thing that we need to do is to see if there is a difference between these rank values. Remember, if we've got a perfectly positive correlation, we would expect to see no difference between those rank values. So all we need to do here is take the difference between these two. And then the next step is to square these values. Just be careful. I don't know why, but some scientific calculators don't return a positive when a minus figure is squared. And now we've got most of the data that we require to put into our equation. We just take a look back at the equation at the top. Spearman's rank is 1, take away 6 times the sum of d squared, divided by n cubed to take n. Now n represents the number in the sample. So how many pairs of data you have, and in this instance we've got 10. And the sum of d squared is simply adding up all of the figures in that column. And we're nearly there. So now we just need to put these numbers into the equation. We've got 1 take away 6 times the sum of d squared, which we've got as 60, divided by the number in the sample, cubed, take away the number in the sample. Okay, so that's going to be 1 take away 360 divided by 990. And then 1 take that figure. We're going to round that to 2 decimal places. I've got a Spearman's rank value of 0.64. As with any statistical test, that figure on its own doesn't mean anything, and that figure needs to be compared to the critical values table. Again, all you need to do is type into search engine Spearman's rank critical values table, and a huge table will come up, and you just need to go and have a look at how many pairs of data. Of course, our pair of data is 10, and we reject the null hypothesis if our Spearman's rank value is greater than the critical value. So I've just sketched out here, just copied off from a table that I found online. 10 pairs of data. We would reject the null hypothesis at the 0.05 significance level if our figure is greater than 0.56, which of course it is. We want to now go to see whether we can be 99% sure that this relationship, this correlation, has not occurred by chance. So we would reject the null hypothesis at this significance level of 0.01 if our Spearman's rank value calculated is greater than the critical value, which of course it is not. So what that means is that we're going to reject the null hypothesis at the 0.05 significance level, which suggests that there's a 95% chance that this relationship did not occur by chance.